And we'll start chapter 6 in first couple days next week before break. So we're going to look at 2 problems. Melanie has 5. Yeah. And Gabby, you did 8, correct? Yeah. So we're going to look at 5 and 8 so you can kind of see the process just to kind of think about what to find when you're doing these graphs. So Melanie, if you good? Yeah. So again, Melanie has number 8.
Okay, so the original function is 1/3 times x minus 5 times x plus 2 times x minus 3. And so what I did first was I found the intercepts, and when you find them you get 5, 0, negative 2, 0, and 3, 0. And then I made the table, and you have to find points beyond and between your intercepts. And so that was that. And then when you look back at the original function, you see that the leading coefficient was 1/3, which is positive. And then you have 3 factors, which is odd. So your graph, the left side of your graph will be going down, and your right side will be going up. And then to find the maximum and minimum, you just plug it into your calculator, and I got negative 0.08 and 10.01. And then for the minimum, 4.08 and negative 2.01. And then the graph looks like that.
Any questions with number 5? So she did all the pieces of the graph, found the max and min with the calculator. Questions? That's great. Gabby has number 8.
I had number 8, which is fx equals 0.2 parentheses x minus 4 squared x plus 1 squared. And first I found the intercepts, which were 4, 0 and negative 1, 0. Then I found the points in between, and the max was 1.5, 7.7, and the minimum was negative 1, 0 or 4, 0. And this is what the graph looks like.
Any questions on number 8? Today we're going to talk a little bit more about those turning points, the max and the min. And also getting the x-intercepts using the calculator. So in your packet, if you could turn to the last page. Okay, 23. The front of the last page. And actually, I lie. Let's look at 22, because I think there's 2 definitions on 22 that we'll talk about. So if you go down halfway through 22, it talks about a local max and a local min, a local maximum and a local minimum. And you were asked to find those values for 15, 17, and 19. They gave you the picture, and you were just asked to estimate it. was question 1 of your homework. And I think the local minimum was question 2 of the homework. See if you can look at your homework and kind of see what you put for your homework for local max. Julia, what did you say for local max?
For local max, I said that it is the y coordinate of a turning point of a function and is higher than all other y points.
Perfect. So she said it's the y coordinate of the turning point of a function. And it's the highest of all the points that are around it. So a max occurs at the y value, because it's the highest point of the graph. But it's the highest point of the graph when you're looking at the turning point. There we go. The turning point is the curve. So the y value of the turning point, and she said it's the highest of the points around it. And there's a little diagram, and in that little diagram you see it's kind of like at the peak. So if you're on a mountain, the highest point of the mountain is considered a local maximum. And the word local is there because the maximum of the graph is technically at positive infinity. This graph goes to positive infinity. The lowest point of the graph is really at negative infinity. Every polynomial is going to go to positive infinity and negative infinity at some point. So when we talk about the local max, we want the area where it turns. And what's the highest point of that area where it turns? And you're looking at the peak when it's the max. The minimum would be the opposite. So again, it's the y value of a turning point. So the turning point is the curve. But it's the lowest of the points around it. So in this case, you're looking at the lowest point of the valley. So the valley of the curve, where is the lowest point of that location? And that is called a turning point. So turning point is where it curves to go from one point to the next. The highest of the points would be the max, the lowest of the point would be the min. So max is always at the peak, and the min is always at the valley. And then right underneath it, it talks about turning points, which we talked a little bit about yesterday too, with the worksheet, the calculator activity. So it says the graph of every polynomial function with a degree of n. So if it's a 5, it's a 10, it's a 15, whatever the degree is, the largest power, it has at most n minus 1 turning points. So it's going to have one less turning point than it does to have powers. And that's because if you have 5 points, it's going to turn 4 times to connect to those 5 points. Moreover, if a polynomial function has n distinct real zeros, then it has exactly n minus 1 turning points. So sometimes a graph might have a power of 5, but we might not have 5 zeros. But this says if we have exactly 5 zeros, then no matter what, I have to have 4 turning points, 1 less. So the number of zeros kind of correlates the number of turning points that we have. So if you flip it over and take out your calculator, I'm going to show you how to get the x-intercepts with the calculator, especially when it's not in factored form and it's not something we can factor. So not everything is factorable. We kind of learned that last chapter, that not all functions can be factored. And if it's a quadratic, we have the quadratic formula to help us solve for x. But sometimes we don't have the quadratic formula because it's not a quadratic. And we don't really have another option to get x besides to rely on the technology. So we are going to graph the function. There's a little picture shown below, but we're going to graph it as well. And we're going to see if we can get the x-intercepts and the max and mins, which the max and min part you did last night for your homework. So if you plug that in your calculator, it should match the little graph that I have down below. But let's put this in the calculator so that we can get those x-intercepts. Was it x cubed minus 4x squared plus 6? So x cubed minus 4x squared plus 6. And then when you hit graph, you should see the picture that is already in your notes, but kind of there for us to look at again. It asks us to find the x-intercepts, the zeros, the solutions. All of those words mean the exact same thing, but it specifically says x-intercepts of the graph. So if I look, how many x-intercepts does this graph have? Julian? 3. So it crosses the x-axis 3 times. So we need to find 3 x-intercepts. And of course there's a function on your calculator that does that for you. So if you hit the second, and we're doing the trace again. So that second trace we use for max, we use for min, and we can use for an x-intercept. So if you want to remind yourself, back here, we're hitting second trace, and then we are using the 0 function. So the calculator, that second trace, we'll use that a good bit. Because there's a couple of different functions in there that it'll help us find pieces of the graph. So second trace, and then number 2 is our 0 function. Way back when we began the year, we used number 5 to find out what graphs intersect. So now, like 2 through 5 are things that we've done with the calculator this year. So we're going to look at number 2. And it says left bound, and a lot of these need you to kind of like trap a value in between. And this is where it's a little confusing. So right here is my x-intercept. The left bound means you need to put a value that looks like it's to the left of that number. So it looks like my x-intercept is close to what? Just by gauging. What would you say the x-intercept looks like it's close to? Melanie?
1.
Positive or negative?
Negative.
Negative, yeah. So it looks like this is close to -1. So for the left bound, we need to pick a number that is on the left side of that. And you're actually going to type in a number. So you could type in a -2, you could type in a -1.5, but it needs to be something that is to the left. So this to the left of -1, maybe we'll try -1.5. So we're actually typing a number in here and then hitting enter. So it's trapping my x-intercept then, and it's saying my x-intercept should be to the right of that value. So there's a little arrow now up there. Right bound means I need to pick a number slightly to the right of that point. Well, right here's -1, so maybe -0.5 would be to the right of it. You could use 0 as well. But you're typing in a number so that when you hit enter, I now have 2 arrows that are pointing toward each other. That means my x-intercept should be in between them. You never hit anything for guess besides enter. And then it gives us the x-intercept, which it was close to -1, but it isn't actually exactly at -1. So using 2 decimal places, it looks like -1.09, and then the y value says 0, because that's what the x-intercept happens. You have an x value when y is 0. So 1 point is -1.09, 0. So we have 3 x-intercepts. One of them is at -1.09. So let's see if we can find a second one, because we've got 3 of them to look at. So if you go to the next one, you have to go back second trace. Every time you have to hit second trace. And we're doing the 0. What number would be a good number to plug in for the left of this second x-intercept? So what number looks like to the left of it, Holly?
1.
Yeah, so let's type a 1 and then hit enter. And Holly, a number that looks like to the right of it would be 2. Hit enter. Nothing for guess. Hit enter again. And then it gives us our second x-intercept. And that looks like it's 1.57. So we're going to do that one more time so that we get 3 x-intercepts. So back to second trace. We're finding the 0, because a 0 is an x-intercept. It is a solution. It can be a factor. And looking at the x-intercept, pick 2 numbers, one that's to the left and one that's to the right. So Matt, what number would be to the left of this last x-intercept? 3. And what number would be to the right? 5. You could say 4, as long as it's to the right of it. Hit enter, and it says it's at 3.51. So our third x-intercept, 3.51. So because none of these are nice, beautiful fractional or whole number values, that's another reason that it wouldn't be factorable. So when you factor, you get nice answers. You get a 1, you get a 1/2, you get a -3/4. But if you can't factor, the answers aren't nearly as nice. They're just decimal values. So this graph has 3 x-intercepts. It has 2 turning points. And you can see that in the picture. So we found the x-intercepts. Now it asks you to find the max and the min. So we've got the x-intercepts. Let's see if we can get the max and the min. And we'll just kind of go through that again. So going back to the calculator, using that calculator a whole bunch today. So second trace, let's find the maximum first. Doesn't really matter. You need to use that little arrow guy, trying to get the highest point of the graph. So that's the local maximum. And remember, your little cursor needs to be to the left of it. You could also try and enter numbers in there manually if you wanted to. And the little cursor needs to be to the right. And then hit enter. And the calculator finds the max to be, anybody get this crazy number? A couple of you? What else? If you didn't get this, Rebecca, what did you get on your calculator? You got this? Who didn't get this number? Abby, what did you get?
I got 1.032.
But does it still have that E guy on it? Yeah. Does anybody know what that E means? Times 10 to the -7, which technically, what number could you say it is, Odette? So if you have this number times 10 to the -7, like what could we say that number really is? 0, yeah. Did anybody get the calculator to say 0? Anybody's calculator said 0? So in theory, the maximum value is, I guess, slightly off. It's not technically at 0, but for all intents and purposes, if I have a number times 10 to the -7, it's pretty much 0. So we would say our maximum, so if you have this E to the negative, and your number isn't quite the same as mine, but if it has an E with it, the calculator just can't, for some reason, focus in on that 0 value. But we'll say that the maximum is at 0, and then it was at 6. So when you have that E, it really means the calculator's trying to get it to the value of 0. So our max is now at 0.6, pretty much on the y-axis. It's our y-intercept up at 0.6. See if you can calculate the min using the minimum function. So second trace, we're getting number 3 this time. And that little blinking guy, the left of the lowest point and the right of the lowest point. So it looks like 2.67, bless you, and 3.48. Two decimal places is always a good thing to use. Instead of just totally rounding it to a whole number or even to one decimal place, it's a little more precise if we have 2 there. Questions? Questions with the calculator, getting an x-intercept or a max or a min. Was anybody not able to get those? So we're going to skip the problem at the bottom and look at the little word problem on the back. So this problem is talking about making a rectangular box. So think about a gift box that you probably have in your house at this point. Our box is cut out of a piece of cardboard that is 16 by 20 inches. So we have this rectangular gift box. The box will be formed by making cuts shown in the diagram and folding up the sides. So if you were actually making your own gift box, which I mean you can get 3 at the dollar store for $1, so why make your own? But maybe you have fancy cardboard that you want to make your own gift box. So you have this piece of cardboard and you're cutting the corners so that it actually forms a box. And mine's in color, so it makes it a little easier to see. But now I have this bottom of the box where maybe I'm going to put a shirt in it or a picture frame or something to go in the box. You want the box to have the greatest volume possible. So of this piece of cardboard that's 16 by 20, when I fold it, I want to make sure that all the space inside is the maximum amount that I could possibly have. So the first thing that we have here, it says how long should you make the cuts, meaning how deep into the cardboard should this little slice go? What is the maximum volume? And then what will the dimensions of the finished box be? So we're going to see if we can try and answer those questions. We're going to use the calculator to help us do that. So the first thing that I'm going to go to is question number 2 here. What is the maximum volume? So our end goal is to get the maximum area, space, volume in this box. And we talked about volume before, earlier in the chapter when we were trying to find the volume of a planter. Because we were putting dirt in it and we wanted to have the volume that was inside. So how do you find a volume? Julian? Right, length, width, height. So if you look at the diagram, the length, there we go. I have this 20 inches down here. So the whole piece of cardboard currently is 20 inches. But we have to fold up each side so that we have sides of a box, because right now it's just a flat piece of cardboard. And we're going to fold up the left side and we're going to fold up the right side. So the inside length is no longer going to be 20. Instead, it's going to be 20 minus 2x, because I'm folding up a distance of x for each side. So the whole thing was 20. But if I have sides to it now, it's no longer going to be 20. It's shorter on the inside of the box. So think if you go home and take apart a box. When you take it apart, it's going to be bigger than what it is put together. So we have 20 minus 2x for each length of the side that you then fold up to get a distance. The width, Odette, what do you think the width would be?
16 minus 2x.
Yeah, 16 minus 2x. Because if I do the same sides to the length to fold up to get sides, I have to do the same side or the same thing to the width to fold it up to get the sides. And the last thing then is the height. Well, once it's folded up, how high would be the side here? What would be the distance to the height? X, yeah. So now we have 20 minus 2x, 16 minus 2x, and then x. So I'd like us to get this in standard form, which would be foiling it together, just kind of to go through that foiling process as a little review. And then we're going to see if we can put the standard form in the calculator to try and find the maximum volume. So when you're foiling, I would ignore the x and do the x last. So I would worry about taking this information here first, getting these two multiplied together. So Mackenzie Myers, 20 times 16 would be 320. 20 times negative 2x. Negative 2x times 16. And then negative 2x times negative 2x. Good. All of this is still times x. I just can't fit mine in. So we have 4x squared minus 72x plus 320. And that's all times the x that was originally there. I'll just bump mine in front. So 4x cubed, 72x squared, 320x. So we're going to see if we can plug this in the calculator. Our goal is to find the maximum volume. Where do you think the maximum volume is going to be located if we're looking at a graph? Just take a guess. Where do you think the maximum volume would be? Odette? Yeah, at the maximum point. So it's going to be at that turning point. So if I'm finding a maximum volume, it's probably going to be somewhere on the maximum of the graph. So we're going to see if we can graph this. And we're going to try and find the maximum location of the graph because that's probably where the maximum value is going to be. So 4x cubed . 72x squared, 320x. So I currently have, looks like a vertical line and then another line on here. And polynomial is supposed to be curves. And that's because the numbers in this graph are so big, because we're talking about 4, 72, 320, that not all of it is going to appear in our little calculator screen. So this is the tricky part. When you're dealing with a graph that doesn't fit in your screen, we're going to see if we can force it to fit in the screen. I'm going to change my x to be maybe like -2, -3, because we don't really need a negative value. X can't be negative. So I can even make it 0 if we wanted to. I'll just go with -2. And maybe we'll change the max to be 15 for now. And this is just me kind of like just doing a little bit of guess and check here. We don't need a negative y value either, because a length can't be negative, a volume can't be negative. We're talking about a physical shape. You can't have a negative amount. And then for the y max, this is the one that we're going to have to change to be bigger so that we can see the highest point of the graph. So pick a number, start somewhere. Start at 100, start at 1,000, start at 500. You just need to pick something. So maybe like 250. I don't know, pick a number. Hit graph. I can see more of the graph now, so that's good. But our goal, Odette said, was to see the max, and the max is still way up here in my calculator screen. So I'm going to go back to the window. I still need to have a higher y value because I still can't see the max. So going back to y, maybe double that. So 250 didn't work. Let's just double it. Let's try 500 and see if that works. And then hit graph. And now we have a max. We're not worried about the min because it says we want the maximum value, not the minimum value. So see if you can trace that. Once you see the peak, do second trace and find that maximum value. And then we'll talk about what that maximum value means. Second trace, get to the left of the top point, get to the right of the top point, and see what value you get. Julian, did you find a maximum value?
Yeah.
What'd you get?
2.95 and 420.01.
Okay, so you said 2.95. And what was the other one?
420.01.
Just 4?
No, 420.1.
420. Okay, I'm sorry. Like, gee, that doesn't sound like a very big box. Okay, there we go. Any questions about getting that value? Sorry, Julian. So we have to decide what this means. So here's x, this is y. What does the x mean? So if I look at the 3 questions, how long should you make the cuts? What is the max value or volume? What is the dimension of the finished box? What does that x represent? Julian?
The length of the cuts.
Yeah, that's the length of the cut. So that's how far we should cut in to get these sides to fold up. So probably we're going to make it closer to 3, but this is saying 2.95. I mean, I don't know if you can be that exact. When you cut it, you're probably going to make it 3 inches. The second question, what is the max volume? Yeah, the y value is the volume because my equation was set equal to y, or volume. So any equation, it's y equals 4. Well, in this case, the y represents the volume. So the max volume would be 420.11, and then we are in inches, and that value is cubed. Volume is cubed. So the max volume is about 420 cubic inches. That's the y. So the x gives us how far we should cut. The y is the volume. The last question says, what will the dimensions of the finished box be? Well, we have x. We have an equation. We can plug that x in to get the dimensions of the box. So we know that it should be 20 minus 2x for the length. The width is 16 minus 2x. And then the height is just the x. And again, it's roughly 3. So once you find x, you can plug it in for your formula in the length, width, and the height. So approximately your dimensions would be around 3 for the height, 14 for the length, and what about 10 inches for the width? Questions? So the calculator is a really cool tool. That's a lot for us that we still can't do algebraically. I'd say once you're finished with math, high school math, you're going to be able to do a lot of that by hand without using the calculator. Every year you're going to learn a little bit more that you can do by hand that you pull away from using the calculator. So on this worksheet, 2 through 13, there's no work that you're really doing for those. So you're determining the number of turns just by looking at that largest power. You're determining the exponents for 8 through 13, and you can put that right on that paper. The 6 graphs, I would like you to please put your work on a separate piece of paper for those 6 graphs. And those graphs would be graphing exactly like we did yesterday. So that little third sheet of paper, find the x-intercepts, find a table of values, get the end behavior, and then your max and your min. On the back, the 23 through 28, let's just do the odd problems there. You don't need to do a million of those, that's just using the calculator. So the odd problems on the back, 23, 25, 27, and then that's it. So you have a little bit of time, where I think right now in 4 minutes you can easily answer 2 through 13. You might be able to like even do those 3 calculator problems on the back if you'd rather start there, do the 23, 25, 27. Get the calculator problems done.